Hello and salam, respected judges. We'd like to thank the competition committee for giving us the opportunity to present. Our project title is An Innovative Technology for Automatic Cleaning of Solar Panels for Increased Energy Efficiency. Our team consists of Mr. Abdurrahman, Mr. Asad, me, Mr. Miswar, and Mr. Musab. Our mentor is Professor Jonathan. This is the outline for our presentation. Solar power provides clean energy with zero carbon emissions. However, there is an issue which greatly reduces the feasibility of solar power. It is the accumulation of dust. When dust is gathered on the solar panels, it greatly reduces its output power efficiency. The current solar panel cleaning techniques are manual cleaning, which requires human labor and also wastes a lot of water; robotic cleaning, which requires extra power for robot operations and can also suffer from mechanical failures; water droplet cleaning, which is a relatively new method, but it also requires water, which is a valuable resource. We propose the utilization of an electrodynamic screen. An EDS is basically an arrangement of electrodes embedded in a dielectric film. When the electrodes are powered by an AC supply, electric field is generated between them, and the coupled operation of electrostatic force with the fringing effect repels the dust particles from the surface of the screen. The EDS works with both charged and uncharged dust particles.
Now, let's summarize and define what exactly we would like to do. We would like to develop an EDS design to solve the dust issue. Not only this, but also optimizing the design of the EDS by trying and testing different electrode arrangement for the phases of the EDS. The main goal is to lower the material cost by using less material, low power consumption, and high efficiency of the cleaning. Now, let's go deep into the theoretical analysis for developing EDS. First of all, we would like to understand what really causes the dust to remain on the surface. The table on the right is showing the average characteristics values for the dust and well-known constant which will be needed. And remember that our goal is to remove the dust from the surface, right? So it's important to understand what are the forces that causing this dust to settle or to remain on the surface. The body diagram here is studying the worst case scenario in which the electrode are horizontal, or the EDS is horizontal, so the maximum force is applied to remove the dust. The gravitational force is totally downward, and the image force is also downward. So these two forces are causing the dust to remain. We sum up these two forces and we call it F down. We divide F down by Q, and this is the electric field. Now we plot the electric field versus the distance between the electrode and the dust, this distance. So this plot is showing that how much electric field is required at a certain distance to remove the dust or to overcome the electric field that is causing this dust to remain on the surface. And remember that it is in the order of 10 to the power of 5. We will be needing this number in the simulation.
Now we will go over the simulations done in this work. So first, we utilize SolidWorks to build our different EDS structures and EMWorks to carry on the electrodynamic simulations for these different structures. The simulated designs include the parallel, dotted parallel, spiral, Hilbert, and the fractal tree structures. In this slide, we can see each structure and how it is built. We constructed these structures using the same dimensions for the electrode widths and the spacing between them, as well as the height. In the simulations, a three-phase voltage is applied. The applied voltage has a magnitude of 1 kilovolt and a frequency of 20 Hz. Next, the obtained results of the electric field are shown in these figures. Each structure has its own unique distribution of electric field. The main parameters that we will consider in our comparison are the electric field intensity and distribution, the area ratio between the covered area by the electrodes and the total area of that specific structure, and the power consumption. Additionally, here we can clearly see the traveling wave on the surface of the parallel, spiral, and the Hilbert structures. This will provide an indication of how well the electric field is covering the surface. For example, the spiral EDS needs further adjustment to avoid the dead region at the center where no electric field is present. Furthermore, to exactly track the dust particle trajectory and to understand how it will be repelled from the surface of the EDS, the following trajectories are generated for the Hilbert spiral and the dotted parallel structure. It will allow us to follow the path of the dust particle until it is totally removed. Also, it provides the total time by the EDS and the total length of the traveled path before moving away from the surface of the EDS. Then we summarized our results in this table showing the area ratio, the maximum electric field, and the specific power consumption. It shows that the most promising structures are the spiral and the Hilbert, with the Hilbert having less ratio and almost double the maximum electric field when compared to the spiral. The area ratio concerns us since the EDS will be on top of the solar panel, so a less area ratio means that the structure is better in terms of transparency.
So our goal was to design 1 kilovolt 3-phase square wave power supply. Basically, the building block of our power supply consists of an inverter followed by a converter, then a logic gate to generate the 3-phase square wave. For the inverter, we used IC4047 to control the switching speed of the push-pull transistor stage and then to be stepped up by the center tapped transformer. To generate the 1.3 kilovolt that will be switched by the logic gate for generating the square wave, we used Cockcroft multiplier, which generates a DC voltage at the output that is that's a multiplication of 2n multiplied by the input. So for our purpose, we used 3 stages Cockcroft multiplier. To generate the 3-phase square wave, we connected the output of the converter to 3 pairs of push-pull transistors, which are controlled by the microcontroller to control the switching speed and generate a delay that is equal to the period of the square wave divided by 3 between each phase of the push-pull transistors.
As a proof of concept to demonstrate the idea of having electric field repelling the dust from the surface, we performed a simple test. This test was made with 2-phase electrode, parallel electrode. And here is the power supply. It uses the Cockcroft multiplier here, the relays as the switches, and also the Arduino to control the relays. The output from the relay is going directly to the EDS. And here it's showing in the video that as we throw the dust or the sand on the EDS, it gets repelled due to the electric field to the either sides. To conclude the research, we were able to develop complete EDS system starting from 12-volt DC up to powering the EDS with high voltages, 1.2 kilovolt square wave. Not only this, but we also tested different electrode arrangement for having less material cost, power consumption, and higher cleaning efficiency. And as a result, the Hilbert design was showing the most promising results. Thank you.